Ever wondered how scientists balance precision and flexibility when modeling complex systems? Like, how do you create a mathematical model that's both accurate and adaptable? Well, let's dive into a fascinating approach that uses something called maximum entropy to solve this puzzle. Imagine you're trying to predict how proteins fold or how molecules move. You have some experimental data, but it's incomplete. You need a way to fill in the gaps without assuming anything extra. That's where the maximum entropy principle comes in. It's like a mathematical rule that says, make the least biased guess possible given the information you have. Here's how it works. You start with a reference distribution. Think of it as your best guess based on existing knowledge. Then you add constraints from your experiments. For example, if your data says a certain property averages a specific value, you force your model to respect that. But how do you adjust your distribution to meet these rules? Enter Lagrange multipliers, a tool from calculus that helps optimize things with constraints. Picture this: you're juggling multiple goals, like keeping your model simple, matching experimental averages, and ensuring probabilities add up to 1. The math here is a bit like solving a puzzle, where each constraint is a piece that shifts your distribution into the right shape. Let's break it down with an example. Suppose you're modeling how molecules move in a solution. You know their average energy, but you don't have every detail. Maximum entropy says, build a distribution that matches this average but doesn't assume anything else. It's like designing a recipe with just a few ingredients. You use what you have, but you don't guess the rest. Why does this matter? In fields like biology or materials science, data is often incomplete. Maximum entropy gives scientists a way to make informed, unbiased predictions without overcomplicating things. It's the difference between building a sturdy bridge with limited materials versus guessing how to use them. And here's the cool part: this principle isn't just theoretical. It's used in everything from weather forecasting to AI training. By marrying physics, math, and real-world data, it's helping us tackle problems that once seemed impossible. So next time you see a simulation or a prediction, remember, behind the scenes, maximum entropy might be quietly ensuring it's as accurate as possible, without overreaching. Thanks for watching and stay curious. Now let's shift gears. Ever wondered how machines learn to generate realistic images, predict protein structures, or even simulate complex physical processes? Today, we're diving into a fascinating area of research that bridges mathematics, machine learning, and physics. Let's break down how scientists are using equations to understand and control probability distributions. Essentially, the rules that govern randomness in data. At the heart of this work is a clever trick, starting with a rough guess about how data is distributed, then refining it using experiments. Imagine you're drawing a map of a city, but you're not sure about the exact streets. You make an initial sketch, then use compass directions from real-world observations to tweak it. That's what this research does, but with math. The result is a new distribution, P, X, which is like your original map adjusted with real-world clues. The formula might look intimidating, but the idea is elegant. P, X is proportional to your original guess multiplied by an exponential factor. Think of this factor as a set of instructions that tells the model how to spread out its predictions while still staying true to the data. It's like giving a dancer a choreography that keeps them moving gracefully, but within the bounds of the stage. But here's the real question: how do you know how different this new model is from your original guess? That's where the Wasserstein distance comes in. Picture two probability distributions as two piles of sand. The Wasserstein distance is like measuring how much you'd have to move the sand from one pile to perfectly match the other. It's a way to quantify difference in a world where everything is probabilistic. To achieve this, the researchers used a technique called Lagrange multipliers, which is like a mathematical nudge to adjust the distribution while respecting constraints. By bounding the Wasserstein distance, they proved there's a mathematical ceiling on how far apart the original and refined distributions can be. It's like setting a speed limit for a car. Even if you hit the gas, you can't go faster than the limit. This bound is crucial because it tells us how reliable our model is. If the distance is small, we can trust the model's predictions. If it's too big, we know something's off. This work isn't just theoretical. It's a foundational step toward more robust AI and scientific simulations. By mathematically anchoring uncertainty, researchers are building models that are both powerful and trustworthy. So the next time you interact with an AI or see a scientific simulation, remember, behind the scenes, principles like maximum entropy and Wasserstein distance are quietly shaping the future of discovery. Stay curious and keep exploring.